Thank you very much.
Right, thanks, Mark, and good morning, everyone. I'm assuming you can see my screen. Just want to check before I get right into it and
All
everyone
good.
says anything. Fantastic. Yeah, just to preempt this presentation, I guess, Ken's been more than just involved in this. Ken was, I guess, the reason for this work. So, I will get Ken to say a few words in a second, but I didn't recognize you at first, Ken. You look different the last time I saw you. I think we've swapped beards. So yeah, today we've got three brief presentations, and they all center around embodied greenhouse gas emissions in HVAC systems. And I'm going to pass over to Ken to say a few quick words before I get into the sort of the detailed presentation. But the first one will be around the embodied greenhouse gas emissions of the fusion modulaire system. I'll get Ken to introduce that because you know it much better than I do, Ken. Then we'll move on to the second project that we did with Fusion with Ken, which Praddeep worked on. So Praddeep Gobinath is a current research assistant with me. He's just finished his PhD recently. He's going to be presenting that because he knows that intimately in particular. And then Praddeep's also, as I said, just finished his PhD. So that's looking at smart control systems for HVAC smart controls for HVAC systems in office buildings. So I thought it might be relevant to this group to hear a bit about some of the results that he got from that study, looking at the embodied emissions of those systems as well. So what I might do first is just sort of lead into the first presentation, which is looking at the fusion modulaire VPAC system itself and the study we did on the embodied greenhouse gas emissions of that system. This was obviously closely connected with Fusion and Ken, and also another researcher we had involved in that project, Christian Joker, who's obviously not here at the moment. What I might do is firstly pass over to you, Ken, just to maybe provide a quick background and context for the project. That's all right?
Yeah, no problem. Thanks, Robert. Fusion Modulaire was able to obtain some grant funding, 2.5 years ago now, through a government grant program that was around the net zero pathway and target to net zero 2050. And so we're able to then engage with Robert and University of Melbourne around setting up the PhD projects for both Praddeep and Christian. And so that's where everything kind of started once we were able to gain that funding. And then we had a 50-50 funding split between the grant funding and the money that Fusion Modulaire paid into the program to be able to get this research done. But the main goal from Fusion's perspective, and you can see from the image that Robert's put up on the screen, which is excellent, you can see the Fusion Modulaire system is a product that is a complete designed whole system. And the idea behind that is to make it modular so that it's easy for installation, it's easy for maintenance, it's easy for removal or reuse at a later date. So there are a lot of design aspects that Fusion have put into the product to try to make it align better with goals of reduction in whole of life carbon impact of a HVAC solution. And the picture there you can see is the unit in the roof, and that single unit air conditions the entire 2,000 square meter space that sits underneath it up to about a 15-meter height. And we're able to do that specifically because of the air diffusion technology, which is a patented component to the product and the design. And because of that, there's therefore, and you can see it in the roof, there's just that dropper that sticks down below the roof, and that's it. That's the air conditioning system that you see from within the space. So it minimizes the amount of ancillary components and build materials and everything that would normally go into a ducted or other, fabric duct or hard duct or whatever style solution that's required to be able to do this type of building and this type of space. And so what we focused on was the fact that because our product had been designed, and the product was designed probably 15 years ago now, it had been designed to do large volume spaces as a ductless solution. But we realized in regards to embodied carbon and everything, it's a major reduction in the overall carbon impact and life cycle carbon on a project, because not only does it reduce the amount of embodied carbon of the HVAC solution, it reduces the amount of embodied carbon of the actual build as well, because you're reducing, you don't need plant rooms, you don't need as much electrical infrastructure, you don't need as much additional things like fire sprinkler, fire suppression systems that you normally need with a ducted solution. And so there's a whole raft of things that Praddeep and Christian went through and researched for us and worked out and produced with Robert. They've produced some very good technical papers and presentation work and everything from that research. So it's been a very valuable process for Fusion, because we're able to then go to market with a product that we can tell clients is world leading and is definitely a major reduction in whole of life carbon impact to air condition a large volume space. So I'll just leave it there. I think that gives enough background.
Excellent. Thanks, Ken. Perfect. So yeah, that's the context for this project. And so we started off looking at what else had been done in this space, and because you're all involved in this group, I'm sure you're well aware that there's very little embodied emissions data and studies on HVAC equipment and components and systems. And there's also little environmental data around to help us with assessing the embodied emissions of these systems. One of them, I'm sure you're well aware of, TM65, CIBSE, which I was involved with the Australian version of. That's a bit of a guide for calculating embodied emissions of HVAC systems, but it in itself has a lot of limitations, a lot of assumptions are required, and so forth. So we knew that there wasn't a lot out there, and so we were starting from almost like a clean slate in terms of trying to understand what the embodied emissions were of the VPAC system. So the aim of this study was really to quantify the emissions of the Fusion VPAC system to different sizes, which I'll get into in a second. As Ken mentioned, it was ideally whole of life. There are some modules that we didn't include for various reasons. The critical modules were A1 to A3, so you're looking at the production of the system itself, both in predominantly in China for the dropper and components, and then for the VPAC units themselves in Australia and Sydney at Dakin. We didn't include A4 and A5 because they're very project specific. And so we wanted something that was system specific rather than project specific at this point. The next project deals with that a little bit more, which we'll talk about. And then it looks at refrigerant leakage through B1 and maintenance, replacement of filters and so forth through B2 and B4, and end of life. We included C3 and C4 in that as well. So in terms of the approach that we used, so for A1 to A3, and I'm assuming because you're all part of this group, you understand the different lifecycle modules I'm talking about. So I won't go into detail about them, but we're looking at the production of the systems themselves. We looked obviously at quantifying the materials in each of the VPAC systems. So we got some really good data from the Smart Temp factory in China in terms of the quantity of steel and aluminium and so forth in the droppers themselves where they're produced. We had some greater challenges in getting data from Dakin. So we had to use some assumptions with the data there, and we used some data from other EPDs and PEPs from France and so forth to supplement the data that we could get to get as much information about the quantities that might be used in those systems as we possibly could. Because as you can probably understand, the VPAC systems are quite complex, lots of components, different materials and so forth in them. We weren't able to, get one, pull it apart, weigh each component out, and that data wasn't necessarily forthcoming from Dakin at the time. We also had data from the energy use in the factory in China as well. So that was supplied to us, which was great. And we also had information about transport distances from that factory to port, shipping distance to Australia, to the distribution centre in Australia as well. And we also had information on material wastage, which we accounted for also, particularly through the dropper assembly in China. So they were I've pretty much mentioned all of these already. They were the sources of the data that we used. So factory-specific data, some, generic data that was available in EPDs and PEPs, eco passports, and then we applied those quantities to embodied emissions coefficients from both the EPIC database, which, as Mark mentioned, I've presented here before, and that, without going into it in a whole lot of detail because we haven't got a lot of time, that provides a much more comprehensive assessment of the embodied emissions in the different materials that are used in the systems. It uses a hybrid approach, so it fills the gaps that exist in traditional inventory data that appears in EPDs and product passports and so forth. And then we also use some eco-invent data where we didn't have any data within the EPIC database for some of the materials and components. The EPIC database is very construction specific, not necessarily technology specific. Then for the use stage, so we're looking at the B modules, we assumed the life of the system was 20 years. We calculated refrigerant leakage, and that's based on real data from the systems that Fusion currently have installed, and the typical leakage rate that's occurring, and that's monitored, throughout the life of these systems. So we had some really good data on that, which is much lower than the leakage rates you might find published elsewhere. We also then included the annual maintenance of B2, which included filters. We used a pure input-output value for this, so there was very little process data for the maintenance stage and the individual filters themselves, so data that might come from EPDs, for example. So it's based on the price of replacing the filters and other maintenance required at that point. There's a limitation with that, obviously, but many studies don't include it at all. So the fact that we've included it is obviously a positive thing. And then B4, which is the fans and dampers and things like that, maintenance of those, replacement of those, and also the replacement of refrigerant during that 20-year period. Was also included. So for the fans and dampers, we assumed a 15-year life. So there's one replacement within that 20-year assessment period that we considered. And then, as I mentioned earlier, we considered C3 and C4 end of life stage. This was really about processing and disposal of the waste at the end of life of the Fusion systems, as well as the impacts associated with the leakage of the refrigerant throughout that 20 years, based on a 3% leakage rate. And then we use data from eco-invent for those components in particular. The EPIC database doesn't have any coefficients for waste or refrigerants, so we use pure process-based eco-invent data in kilograms of CO2 per kilogram of material disposed of. And then that's the results that we came up with. So when we combined all of these modules together, the calculation of the embodied emissions, I forgot to mention earlier that there were two systems we looked at. So Fusion have a 135 kilowatt and a 180 kilowatt system. So we looked at both of those, slightly different material compositions and quantities. And obviously the 180 being a high capacity unit has a slightly higher embodied emissions. So they're the final numbers. Those numbers probably don't mean a whole lot to most of you here, but just to give you a bit of an equivalence, and lots of equivalents that we could do, that's about 40% of the emissions of building an average size new house of about 240 square metres in Australia. So substantial amount, predominantly because we've got a lot of metals in there, which are typically highly emissions intensive. So here's a breakdown of the different materials within each of those systems. A lot of steel, aluminium emissions coming in, as well as some other materials there. But also shows that there are a lot of opportunities for reducing emissions. And with any study like this, it's an opportunity to identify where the lowest hanging fruit is and where you can achieve significant reductions in emissions. So I know Ken and Fusion are really interested in actually identifying ways of reducing the emissions, now having this information. And if you don't have this information, it's really difficult to know what you should do to reduce emissions and where the low-hanging fruit is. And we've got processes now in steel manufacturing and aluminium manufacturing to significantly reduce emissions. So there are opportunities, I guess, that Fusion may look at into the future. And Ken, you may also be already considering. So when we combine everything together, these are the sort of life cycle emissions of the two systems. You can see obviously that the emissions for the 180 kilowatt system are slightly higher. End of life stage is the lowest contributor, whereas the product stage, the A1 to A3, is the largest, obviously through the manufacture of the system and the metals particularly that are required. And then use stage, there's a not insignificant contribution from the refrigerant requirements as well. And then I guess the final outcome of this study was the production of a climate declaration. So it's akin to an EPD, but it focuses just on global warming potential. So we produced that. It's not registered or anything at this point, as far as I know, but it was an output of this study, which I guess makes available to the public the critical information in terms of being able to then look at how this system performs from a life cycle perspective across most of the life cycle modules, and then, most importantly, potentially compare this system to other alternatives. And that's where the second I won't go through these because they're sort of just findings that I've already mentioned, but the second project that we worked on with Ken comes in, and it's really about looking at, okay, we understand how the fusion system operates across the life cycle. But what we want to know is how it compares to alternative systems. And as Ken mentioned, there are so many benefits of the fusion system in terms of reducing the emissions of the system itself, but also the whole building. And so the second project looked at developing a tool to be able to compare fusion system to alternative systems. And so I'm going to now pass over, unless there's any critical questions, I'm happy to answer questions now or at the end. I'm going to stop sharing my screen and hand over to Praddeep to present that project.
Rob, I'm just thinking, like, I want to make sure that we get enough time for Praddeep's presentation as well. But if we just allocate maybe sort of 5 minutes now, because I think we might lose some of the questions otherwise as we move on to a new topic. So, yeah, maybe give people an opportunity now to fire away.
I've noticed there's a couple of questions in the chat. So
yes, that's true, Ken. Look, Adrian's put his hand up very politely. Yeah, come on, mate, just jump in. It's all right. But always very polite. Go for it, Adrian, and then we'll look at those chat questions as well.
Yeah, no problem. No, that was fantastic. Thanks both. No, just a couple of additional questions around the refrigerant, because I saw it mentioned there on the A1, A3 as let's say a slice of the pie. I was just wondering if you could add some actual numbers around that in terms of what that looks like in terms of assuming it's the production of the refrigerant being R410. And then the second question was whether there was any numbers around the destruction of refrigerant, whether that was included in the process as well.
Ken can probably add to the source of the data, and then Praddeep, probably you can add to the emissions intensities that we used.
So from the R410 refrigerant is in the modules that are used as the condenser modules, which are Dakin product condenser modules. So all of the data it's a bog standard Dakin VRV module. So the data is straight from Dakin in regards to any of the refrigerant information there. From a maintenance perspective, the refrigerant leak rate is actual reported data from our maintenance team on the amount of maintenance work and replacement of refrigerant that occurs annually due to leakage in the equipment. So because it's a pre-factory built product, there's very, very minimal leakage because it's a complete tested, commissioned, so in factory, the product is run up and commissioned before it's shipped to site. So there's no on-site, brazing and all that sort of work. So we don't have that typical additional leakage rate or loss of refrigerant that would normally occur in a normal HVAC installation where you're brazing pipe work and doing all that sort of work on site. As far as at the end phase with destruction of refrigerant, we actually haven't so far pulled down a unit and pulled it apart, but our maintenance team would normally do reclaim of refrigerant in most instances. But how that fitted into the calculations and everything, I'd actually have to defer to Christian or Robert around that bit, because they threw that into the calcs and everything.
No problem. Thanks again. That's really helpful. And it's a bit of a loaded question because it's really hard information to get. So I'm trying to work out if anybody's got it. It's basically where I'm heading with it.
Yeah, we have it because we build the product, we maintain the product, we sell the product, we install the product. So as a contractor / engineering / install maintenance company, it's all our data because we do the whole process. And I totally understand, Adrian, the biggest problem you've got in the industry is we are unique as a business because we're end to end as a business, and the HVAC industry is not an end to end, industry. It's a, completely broken up industry into there's a supplier, here's an installer, here's the maintainer, here's the BMS people. They're all separate entities and parties, and they all do or don't collect data depending on their contracts and their agreements, and then they won't share it and all that sort of stuff. And even we had trouble as a partner purchaser through Dakin. We had trouble getting detailed data out of Dakin for a product that they manufacture directly for us. So it's not easy.
No, that's really helpful. Thanks. I'll leave it there. Thanks, guys.
Thanks for that. Look, Jess did
I'm going to have to duck off.
No worries, Ken. Take it easy. Thanks very much for joining us.
Thank you.
Jess did ask about the refrigerant leakage rate, and Ken replied that it's from the maintenance team's annual reporting. So I think that one was covered. And I guess, look, maybe Praddeep, if you want to jump in now, and that way we make sure we've got enough time for you, and then we can continue with questions after your presentation.
I don't think your mic's working, Praddeep. We can't hear you. Still not.
Can you hear me
That's
now?
better. Yeah, that's it.
All right, cool. Sorry about that. Okay. And can you guys see my screen? Yep. Hello.
All good. Yep.
Yeah, cool. Right. So I'll continue from Rob's presentation. As Ken described earlier, Fusion Modular, they've developed an Excel-based tool to quantify and compare the operational performance of the modular VPAC units with alternative HVAC systems for large volume spaces. And so, us from the University of Melbourne, our aim was to propose an approach that would allow for a streamlined quantification and comparison of the embodied greenhouse gas emissions for these systems. And hold on, is it lagging? All right. And so this figure shows the overall calculation method. So essentially, using inputs provided by the user, the tool calculates the system level coefficient of performance, the peak heating and cooling capacities, as well as the operational greenhouse gas emissions. What we've done is to develop a material library using the EPIC database, which translates the system sizes into embodied greenhouse gas emissions estimates. And this calculation method accounts for most of the main components that make up the HVAC system, depending on the HVAC system configuration that was chosen by the user. Well, I'll quickly demonstrate how this approach works through a simple case study building. So given the building size, location, service life, as well as the heating and cooling loads, the tool computes the embodied greenhouse gas emissions of three alternative HVAC systems, which are the water-cooled chill water system, air-cooled chill water system, and rooftop package units. In this scenario, heating demand is assumed to be met by a natural gas boiler. And the components that are included in the analysis are shown in this table, along with their useful service life in brackets. And for comparison, we've also included the embodied emissions for both the VPAC 135 and the VPAC 180 units. And so these are the results. The figure on your left essentially shows the total embodied greenhouse gas emissions associated with the modular VPAC units, as well as the alternative HVAC systems. Unsurprisingly, the water-cooled chill water system recorded the highest embodied emissions, followed by the air-cooled chill water system and the rooftop package unit. We've broken down these embodied emissions based on the type of components, namely source, distribution, delivery, control, and refrigerants. And as shown in the figure on your right, the distribution system, which includes ducts, fittings, insulation, lining, accounts for the largest fraction of the embodied greenhouse gas emissions. And this is primarily due to the large quantities of galvanized sheet steel that's used to produce the ductwork. And as you can see, in the case of the VPAC units, eliminating dedicated distribution and delivery systems offers significant reduction in the total embodied emissions of the systems. We've tried to validate this approach by comparing the estimates given by this approach with manually calculated embodied greenhouse gas emissions that have been reported in past studies. So for consistency, we've used data from the EPIC database to manually recalculate the embodied emissions. And as shown in this figure, the estimates produced by this approach, they are within 10% of the manually calculated figures. And this disparity is probably related to the lack of data points within the proposed approach, but still, it's a rather small margin of error. I'll also talk about some of the limitations associated with this tool. Firstly, only a limited number of EPDs were available at the time we conducted this research for HVAC components and equipment. And so in some instances where we didn't find suitable EPDs, the embodied emissions were quantified using a cost-based input-output data. Secondly, we've omitted some subsystems such as pipes and pipe fittings because we didn't have sufficient data that would translate equipment sizing results into the quantities of materials. And thirdly, and this is probably the biggest challenge that we have, this approach assumes that the embodied emissions vary linearly with equipment sizing. However, this assumption of linearity may not always be accurate. And so, again, this is a major limitation in this approach. But despite these limitations, this approach is still capable of providing quick estimates of embodied greenhouse gas emissions of HVAC systems, which can be beneficial during early stages of building design and system selection. Next, I'll briefly talk about some of the findings from my PhD research. I was supervised by Rob and Professor Traverso from RWTH Aachen University in Germany. For context, my PhD focused on applying the life cycle sustainability assessment method to smart HVAC control systems in office buildings. Today, however, I'll only focus on the findings for the environmental dimension. So the study was conducted to a reference office building based in Melbourne using the geometry and layout of the reference building, as well as the control requirements. The hardware of the control system was determined. In this case, the HVAC system was assumed to be a variable air volume system with hot water reheat, whereas the control system was assumed to be demand responsive based on indoor air temperature and CO2 concentration levels. So to give you an idea, the figure on your right shows the material profile of the control system hardware that was used. Overall, plastics account for the largest share by mass in most components, in some cases reaching up to 80%. Paper products, which are used in packaging this hardware, also make a significant contribution. And by contrast, electronics and metals represent a smaller share, averaging less than 25 and about 20% respectively. And the life cycle greenhouse gas emissions can be categorized into initial and recurring embodied, operational, and end-of-life stages. For the initial and recurring embodied emissions, I use data from EPDs as well as the EPIC database. Whereas for the operational emissions, I accounted for both the use of electricity to run the hardware, as well as any internet-based computing resources. For the end-of-life stage, the emissions were quantified by assuming Australian conditions and practices for waste, electrical, and electronic equipment treatment. And we've also assumed a 50-year period of assessment when conducting this study. And so these are the results as shown in the figure on your left. The recurring phase, surprisingly, which is associated with the replacement of a hardware at the end of the useful service life, that accounted for the largest fraction of the total life cycle emissions. This is followed by the operational and initial embodied phases. The end-of-life phase contributed to less than 1% of the total life cycle emissions. To give you an idea of what that figure represents, on the figure on your right, I've compared the life cycle emissions of just the control system with the operational emissions of the HVAC system over a 50-year period. And what I found was that the life cycle emissions of the control systems were roughly 9 to 10% of the HVAC operational emissions. So throughout this research, we found that both my PhD and the Fusion project, we found that obtaining data on building technical systems was quite challenging. This is mainly due to the complex supply chains and the manufacturing processes involved in their production. EPDs, there are a few here and there, but again, they're very limited. And so what I found was that comprehensively assessing the embodied greenhouse gas emissions of these systems can be very, very time consuming. And to help address some of these challenges, we hope and plan to expand the EPIC database over the next few years to include HVAC systems and eventually building services in general, so that streamlined assessments can be performed rather quickly. Yeah, that'll be all from me. I'll be happy to take some questions. Thank you.
Praddeep, thank you very much. That's excellent. Some really interesting stuff there, and I've definitely got a couple of questions. But first of all, maybe open it to the group. Anything that you'd like to ask, Praddeep?
Oh,
Hi all. I definitely have a couple of questions. Great presentations. Thank you, Praddeep, and also to Rob. Andrew here from AG Coombs, by the way, for context. Some of my questions might have been more appropriate for Ken in relation to the fusion air system. I thought it was a really great study, and certainly looking at the ability to reduce the amount of ductwork is something that we've and the emissions associated with ductwork is something that we've also been looking at internally. I guess my first question was any work done to establish that the fusion air system was exactly equivalent in terms of performance of air conditioning within the space versus the equivalent HVAC systems? Because having a bit of a look at the fusion HVAC system, it looks like it's a high air diffusion system based on swirl diffusers and things like that. And in the past, when the industry's looked at sort of ductless solutions, there's been the exploration of large volumes, have looked at things like the Bauer control system and different methods of air control. Again, this might be a question more for Ken, but was that looked at? Because obviously less equipment is great, but is the air distribution exactly equivalent to having, in a large space that might be a gymnasium or sporting field, having, high air transfer rates and things like that?
Yeah, Andrew, thanks for the question. You're right. It is Ken is the perfect person to answer that. I do know that they've done a lot of CFD modeling and so forth, and it performs surprisingly well. I can't comment on comparability to traditional systems at all, but internally, I guess, is obviously trying to sell the system. He talks it up in terms of its performance compared to traditional systems for certain types of spaces. Yeah, in certain contexts, in terms of up to 15 meters height and all that sort of stuff. But I don't know if Mark, you know any more about the system, or Praddeep, you can comment any more. But that's sort of all I can comment on.
Yeah, I think Ken is probably the best person to answer this question, because it's less about, your question is less about embodied carbon and more about the operational phase. So I think Ken is probably the best person to try and answer that question.
No worries, and I might reach out to him directly after this just to understand. I did have a follow-up question, which was a little bit more on the embodied carbon. I don't want to hog too much time in case someone else has a question, though.
Go, Andrew. Go on. You've got the floor,
I'll jump
mate.
in.
Go on.
It occurs to me that so much of the embodied carbon, even associated with manufacturing of the water-cooled chillers and air-cooled chillers, it's very linked to grid electricity in the countries from which the manufacturing is done. Because, of course, the question I was going to ask is, in terms of operational emissions, we're not looking at them so closely just because we know in Australia, eventually, as the grid decarbonizes, the electricity usage element with respect to emissions is going to go down. But similarly, the emissions associated with the embodied carbon of creating the kit, depending on where it's created, is going to be more or less susceptible to the decarbonisation of the grid in those countries. Obviously, China's moving rapidly. Of course, they've got a long way to go, but they're rapidly increasing their uptake of renewables. So I wonder if there's been any thinking about like a sensitivity analysis to how the embodied carbon of different kits based on where it's been made is also sensitive to the grid decarbonisation in those countries. I know that's quite a complex issue, but it's something which is worth considering, because those numbers will naturally also start to come down.
Yeah, good question, Andrew. It's something we typically consider. This is a very short, constrained project in a way, so we didn't have a chance to look at all the different sensitivities and assumptions and everything like that. But it is typically something we would consider in terms of decarbonisation over time, and there's lots of assumptions you have to make around both operational and embodied decarbonisation. It actually leads to a project we're working on at the moment, which is a global version of EPIC, and that will allow people to select coefficients/materials from different regions around the world if you already know where those products are coming from, and or if you want to compare products from different locations. So if you want to compare a material or a product from China versus Germany versus Australia or New Zealand, whatever, you'll have an indication, okay, where, what are the emissions associated with those materials or products? That's very context, very grid specific then, but also supply chain specific, because there are especially in systems like this, there are a whole lot of components coming together from, in some cases, different countries around the world. And therefore the different the grid intensities will determine the embodied emissions of those different materials and components as they come together into one system. So we'll be able to do that when we've got this global version of EPIC, which is probably going to be released next year.
Fantastic. Yeah, that sounds really interesting. Would love to keep tracking that and see how that goes. But those are all the questions from me. Thanks very much for the presentations. Found it really interesting.
Thanks, Andrew.
Anne's welcome. You can also just shout out. I guess I did want to ask